Hello, hello, and we are going to have a quick tutorial, if I can figure out how to make this work, a quick tutorial on series circuits and how you do Ohm's law calculations in series circuits. All right, so I'm going to start this presentation real quickly. Some of you have already seen this if you've been in any of our Zoom sessions. This is just a quick review over electric charge, electric fields, and Coulomb's law. We did a little tutorial over that last week. And then at the end of last week, you were starting to get into electric current. This is Ohm's law. The voltage equals the current times the resistance. And we're going to look at how this applies to series circuits and parallel circuits. First thing you need to know and understand about series circuits is that there's just one pathway for the electricity to follow. When it comes to applying Ohm's law to a series circuit, you need to know and understand those three white bullets there. The easiest one to start with actually is total current. There's only one pathway for the electricity to flow. It has nowhere else to go. So the current is the same throughout the entire circuit. The amount of electrons flowing is the same throughout that entire circuit. They don't have anywhere else to go. So I is going to be equal at every single point throughout the circuit. Total voltage is provided by the battery or your voltage source, whatever that might be over here. As you can see, the total voltage is 9 volts. Now what we know is that the voltage drops as it passes through every device in a circuit. So the electricity comes out with 9 volts, so to say. Think about that like the oomph, the push that the current has to flow. It's the pressure, if you think about the water analogy. But each time it goes through a resistor, the voltage decreases. And so by the time the current has passed through each of these resistors, we should no longer have any voltage left. So the sum of the voltage drops across each component has to equal the total, which in this case, in this example, is 9. And then for total resistance, that's also pretty easy in a series circuit. You simply add the resistors together to get the total. What I want to show you now is how to complete one of these tables or charts, if we can. And so I think what I'm going to do is pause this screen. And actually share my whiteboard and work this out with you. Let's see if this is going to work. All right, so what I've got here is a very rough sketch of the series circuit. That was the example. A 9-volt battery is connected to 3 resistors. The first resistor is 100 ohms. The second resistor is 300 ohms, and the third resistor is 50 ohms. So I filled in our table over here. The one thing I can do, because this is a series circuit, is add up all of the resistors to get my total resistance for the whole circuit, and that's going to be, what, 450 ohms. All right. Using Ohm's law, let's do this for 1 second. Using Ohm's law here, we're going to apply Ohm's law to the entire circuit first. All right, so I have for the whole circuit 9 volts equals I, the total current, times the total resistance. So I'll give you a second to figure out what that total current is. We're going to divide 9 by 450 and find out that the current is actually equal to 0.02 amps. So that's the total current in the entire circuit, 0.02. Now, from what we understand about a series circuit, that current is the same every single place in that circuit. So there's 0.02 amps of current going through resistor 3. There's 0.02 amps of current going through resistor 2. There's 0.02 amps of current going through resistor 1. Now what we're going to do is apply Ohm's law to each individual resistor, each individual component in the circuit to find the voltage drop for each resistor. So we're going to calculate V. We'll call it V1, voltage 1 that's occurring through resistor 1. We know the current is 0.02, and we know the resistance for the first resistor is 100. So clearly, the voltage drop across resistor 1 is simply 2 volts. So we'll fill in 2 volts here. And then you're just going to repeat. Let's see, let's do the second resistor. So that would be a 300 ohm resistor. And 300 times 0.02, and then give us 6. So we're going to fill in for resistor 2, 6 volts. Now at this point, you should be able to figure out the voltage drop through resistor 3, because the voltage drops for all 3 components should add up to the total of 9. So it looks like it should be 1. But let's work it out and see just in case. So this is a 50 ohm resistor, and sure enough, 50 times 0.02 is going to give us 1 volt. So that's how you fill in the components or the missing information for Ohm's law. Now let's talk about power. Okay, so in blue is the equation for electrical power. Electrical power is the rate at which electrical energy is turned into some other form of energy: sound energy, light energy, heat energy, mechanical energy, so forth and so on. And like other units for power, it's going to be watts. And that's obviously why the light bulbs are measured in watts. It's a measure of how the rate at which electrical energy is turned into light and heat in terms of light bulbs. All you really need to know there is that blue equation: power equals current times voltage. And we have enough as it is now with our almost complete table to just straight up calculate that power. But before we do that, I want to show you the other stuff in green. So in green, we've got Ohm's law, V equals IR. I've also rearranged it in terms of I equals V over R, because sometimes you may not have all 3 variables, but you may still be asked to calculate electrical power. So if you substitute in for V or I in either case for power, you could also get I squared over R here. This is, I substituted in, let's see, I substituted in for V, IR. So that's basically I times R. That's I squared over R times R. Or you could also substitute in V over R for I and get V squared over R. So there are 3 actual equations you would benefit from knowing for power. But since we have everything we need over here, we'll go ahead and just multiply I times V. And for the first resistor, we will see, and we'll keep this in blue, I think, we'll see that the power for resistor 1 is 0.04. And that will be 0.04 watts. I just don't have much room to include that here. For resistor 2, it's 0.12. And all I'm doing is multiplying the I. Oh, did I do that right? Yeah, the I times the V is all I'm doing. That's 0.02 times 1, obviously, is going to be 0.02. And we don't have to total up the power. That doesn't really apply, because what we're going to be curious to know is if these 3 resistors were light bulbs, then which light bulb would be the brightest? It would be the one that has the greatest power. So that would be, if these were bulbs, that would be bulb 2, resistor 2. So that's how you complete one of these Ohm's law type charts or tables. That's how you apply Ohm's law to a series circuit, first figuring out what in total you can determine about the circuit, and then breaking it down one component or one resistor at a time and applying Ohm's law to the individual resistors. Hope that helps, and we'll see you next time.